Okay, great. Right, so in this session, we'll run through roughly this agenda. I'll give an introduction to myself and my background at the hub. And we'll talk about retrofit and the scale of the challenge and how solar PV will play a role in that. We'll look at a bit more how solar photovoltaics actually work, the components of a system, the sort of design we're seeing from various projects. A quick intro on how to estimate energy production from solar PV, and then look at some of the costs and benefits to tenants and the organisations, and as well as a bit into the procurement and as well. So midday on the summer solstice, we probably couldn't have picked a more appropriate time to be talking about solar energy. Longest day of the year. Highest day point of the sun in the sky. So some of the graphs we'll be going through later, our ancestors would have been very much focused on the sun and the seasons, and increasingly as a society we're going to be heading back towards that sort of association with renewable energy as well, and whatever energy may be associated with Stonehenge, it's specifically electricity we'll be talking about today. Okay, so as Alan mentioned, I'm chair of Solar Energy UK's local authority working group. So we fund kind of where we hold quarterly sessions for members representing local authorities and their supply chain, particularly looking at issues of solar PV and local authority and social housing estates. And as well as that, I'm an energy projects manager with the Greater South East Net Zero Hub. That is a public sector team hosted by Cambridge and Peterborough Combined Authority, funded by the Department for Energy Security and Net Zero. And our role is very much to provide day-to-day project management support for local authorities and communities to help accelerate delivery of a whole range of net zero projects. But renewable energy is probably the bulk of that work. So I'm based in East Anglia, but as a team, we cover that whole region on the map there, and there's equivalent teams, across all of England as well in other regions. So this is probably familiar to most people here, but why do we need to retrofit our buildings? There's a whole host of drivers, like the climate crisis, all our climate emergency targets, that are now councils are increasingly adopting, as well as national government policy to improve the housing stock's energy performance. Carbon emissions will very much play into that. Last year has seen a massive boom in solar PV installation as it's plays into energy security. The more power we produce on this island, the less we have to import, whether that's electricity or gas. There's the whole health angle, fuel poverty, cold winters, overheating in summer. Solar PV has a role to play in addressing comfort and health issues as well. And cost of living as well, just in terms of the pound in people's pocket and how far that goes in meeting people's basic needs and services. Pretty much every home in the country needs some improvement in some fashion to make it more energy, improve the energy performance. And in our region in the southeast, it's close to 14 million homes, large chunk of those living in fuel poverty. So the rate of the sooner we get on with this job, the better. And as well, there's going to be a lot of skills and extra jobs needed to help scale up that pace of retrofit as well. Okay, so on to the topic of the day. What are solar photovoltaics? More commonly abbreviated as solar PV. So solar PV, they're an electricity generating technology, and there's plenty of them in the image there. So in this case, these are rooftop mounted solar panels, and a solar panel is basically I won't go into too much of the physics of how it works, but it's a composite panel of layers of silicon and other conductive materials that, when placed in direct sunlight, generates voltage and current, allows the flow of electricity. So when coupled into a circuit and integrated into a grid, it allows the direct conversion of sunlight falling onto a roof into electrical energy to then run appliances in that building. we'll talk a bit about other solar technologies in a moment. But when you break down a solar panel PV system, these are the general most common components you will encounter. So clearly the most visible bit is the panel, whether that's on the roof, over a car park, mounted on the ground somewhere. So yeah, the panel is a modular system. They can be wired up. So one panel is typically around 300 watts of power, and it scales linearly. So 10 panels will have 10 times the power output of one panel on its own, and so on. So you can just scale them up as much as the rooftop can handle, really. Moving along the chain, the next key bit of equipment in the system is the inverter. So that picture there is of an in-roof inverter. So that takes the current that's coming from the solar panel, and it converts it into a different form of electricity that integrates then with the household's electricity system. So it converts it from DC current into AC. So yeah, that's a basic inverter there. You can also get some more advanced inverters which are actually integrated into the panels, which allow for greater output, especially when there's systems at risk of shading. Where you have a single rooftop inverter like the one in the photo, if one panel in a system gets shaded, that reduces the output of the whole circuit. Whereas if you have a rooftop array with micro inverters, then if one panel out of 10 gets shaded, the other 9 are still operating at full output. So yeah, it's little components like that can boost very much the output of solar PV system and are worth the extra investment, arguably, in some cases. Moving on, the next component may be optional. This one you don't necessarily need it, but is nice to have, is a battery system. So again, this is generally installed in the building, either in the loft space with the inverter or in some other utility space. And it allows the direct charging and storage of electricity for use at another time period. Without a battery, you either have to consume the electricity as it's being generated, or it gets exported off the property and back into the grid. The battery gives you the advantage of being able to store that power on the property and then use it later in the day at a time that's when it's useful to the tenant. We'll talk about it also a bit later on, but then with smart batteries and smart inverters, you get into some quite interesting options if you're operating a large housing stock with different small batteries in them. We'll cover that in a bit, but yeah, nice opportunities for flexibility and virtual power plants too. Next bit there, the meter. Increasingly, smart meters will do the job of both monitoring import and export of solar PV, as well as the total generation. And the more data you have available to you, the better, really, both for income purposes, but also those smart energy services will be increasingly relevant in the future. And then the final piece is a bit of a visual interface, either a visual monitor in the home or the building, or an app on the phone or on the computer that gives you real-time information about the performance of the system. So both useful for the homeowner in terms of timing, turning on appliances, but also useful for monitoring fleet-wide performance and maintenance issues as well. Okay. So going into a bit more detail on the panel itself, these are the various kind of variations you might see when you're looking at designing a project. So they basically come in two kind of silicon styles. One is called polycrystalline. So these, when you're seeing them up on the roof, they typically have a bluer and perhaps slightly more varied tone. These are made up of small fragments of silicon crystals, which are then melted together to form silicon wafers. So they have a bit more of a variegated pattern. They're cheaper to produce and to build and purchase. They typically have efficiencies at the lower end of the scale. So they typically output maybe 250 to 300 watts per panel. Conversely, the next type is one called monocrystalline solar PV panels. They're in terms of appearance, have a much more uniform and darker tone, just from aesthetic and architectural purposes. And that's because they're made of pure silicon wafers, like cut straight from a very kind of high quality silicon crystal, and so they're all rather than mixing up different fragments, it's all from the same source. They're slightly more expensive to purchase, but they do produce more electricity. They are more efficient, and current ones on the market for the same kind of surface area would typically output 350 to 400 watts per panel. So in terms of making choices, if you had a very large roof space and cost and size wasn't so much an issue, you could probably maybe look at the polycrystalline option. But if you're more if you have smaller surface areas to work with, then you might want to maximize the output for the surface area, so monocrystalline might be the choice you make. Some other variants you see, bifacial panels are might be an option as well. So these are more opaque or transparent ones, which are able to generate electricity from light coming from both directions of the panel. So they're quite common, or increasingly common in kind of rooftop situations where there may be a canopy or an atrium type space where sunlight is still allowed into the building. You can also get solar thermal panels. These are not photovoltaic. They're basically radiators or tubes which have hot water flowing through them directly. The sun's energy heats the water, and that goes into a water tank in the building. We won't go into much more detail today, but they're certainly useful in some circumstances. But they can be integrated into a hybrid panel, a solar PV thermal panel, PVT, where the same panel has both electricity generation and hot water generation within the same product and the same surface area. So again, in terms of maximizing the benefit from small surface areas, you can arguably get electricity and hot water, two products for the price of one, perhaps. And it's worth mentioning solar tiles as well. So these are actually PV panels, but they're designed in the form factor of a roofing tile, and they will just be integrated in the same roof space along with other roof tiles. They don't stand out too visibly, so they're maybe more preferred for conservation areas, listed buildings where planning and that kind of street scene may be a consideration. Okay, looking a bit wider in terms of the components to actually solar PV system designs, by far the most common you'll see in housing is just a basic single rooftop supplying the home it's sitting on. So these will probably range in size from maybe 4 panels up to perhaps 10 or 12. And in terms of electricity output, that would mean about 1 kilowatt to just under 4 kilowatts of electricity generation from that rooftop. That upper end of the scale, 3.68, that's typically what the export limit is for a single house connecting into the kind of electricity grid. That's kind of a threshold that's been used in the past just to make connections easier. You can get connections and systems larger than that, but yeah, you may need a special apply for a special grid connection. But that under 4 kilowatts is the sweet spot in terms of simple installations and benefit to the householder. You can get completely off-grid systems where the solar panel and the battery are completely isolated from the grid, and yeah, they're just charging up and discharging loads based off that. I don't think that'd be too common in social housing. It's more for kind of mobile homes, caravans, canal boats, that sort of thing. But we have seen it in some council properties where they may be an isolated building that doesn't have a power supply, and there's a use for it there. Where it also gets interesting is shared rooftop systems. So if you have social housing that's maybe in an apartment block or a block of flats, or more of a kind of a denser situation, then shared rooftops may be the only option. So traditionally, where apartment buildings have been integrated with solar PV, we've seen a rooftop array put on the top. That's then fitted into the building's communal supply. rather than the individual flats and apartments. So it might go to the stairwell, the car park, or some other lighting-based circuit. So yeah, it still generates power, still meets some building demand, goes to the grid, but it doesn't necessarily benefit the tenants or the homeowners directly. There's been quite a few projects and technology developments which are trying to solve this problem. How would you get a shared rooftop array supplying multiple flats and dwellings within a apartment block? One in particular is a product called Solshare. This is a really interesting piece of kit. It's basically a bit of hardware. It's an extra box that sits next to the inverter. And what it allows to do is one single large rooftop array can then be split into 15 individual flat electricity supplies per Solshare unit. So that means coming out of the Solshare box, a electricity feed can feed out into the supply for an individual flat, which that tenant can then use to power their appliances and heating systems directly. This means that it does count towards improving the EPC of that home and dwelling. So it's hopefully a solution we'll see more of going forward. There's other companies looking at trying to do the same thing, but more of a software basis. So companies like Urban Chain are looking at blockchain solutions, and there's a few others out there. But yeah, definitely look in this space. Just because it's a communal building doesn't mean the people can't get directly benefit from a shared array on the roof. So moving on to how would you estimate solar PV generation? This diagram, this map here, it shows roughly the spread of solar radiation, solar energy running north to south across the UK, across the country. Obviously, closer you are to the equator, the higher the sun is in the sky, the more solar radiation is hitting that rooftop. And then conversely, moving northwards towards the pole, up into Scotland, that strength of the solar energy reaching the Earth's surface is slightly weaker, but still useful. So it doesn't really matter where you are in the UK, it's going to be worthwhile. As a rule of thumb, this equation here I've got on the screen, you can basically assume 1 kilowatt peak of solar panels will generate roughly 1,000 kilowatt hours per year. And you can just use that as a ratio to multiply up. So 2 kilowatt peak would generate 2,000 kilowatt hours, 10 would be 10,000. There's pluses and minuses depending on exactly where you are. On the very south coast of England, you could maybe even get away with a factor of 1,100 kilowatt hours per kilowatt peak. In Scotland, it would be slightly lower, 850. But as a quick approach, that's a good guesstimate of what a solar rooftop would produce. That's if it's also I should mention at an ideal angle to the sun, and also facing due south. There will be a bit of production drop off if it's away from that ideal orientation or angle. There's also software packages available that allow you to do much more detailed half-hourly modeling. So software packages like the PVsyst OnGen, they have databases of real-time weather data for every location across the country. So you can specify a solar panel system with a particular alignment at the particular location, and then it will simulate for every half-hour period across that year what that PV system would produce. So if you're doing a more detailed business case, this sort of software is very useful for getting some much more accurate and detailed output numbers to base your investment on. So in terms of the sort of electricity you're going to see coming out of a system, anyone monitoring a solar PV array will start to become very familiar with shapes and graphs looking like this. So this main picture here, this is actually what's up on my roof at the moment. I took this screenshot a couple of days ago on a very sunny June day, and this is the typical generation curve you would see like throughout a 24-hour period. Obviously nothing at overnight, but as the sun rises, gets higher in the sky, So yeah, the solar output of the system will increase, peaking for a period around lunchtime, midday, and then diminishing again as the sun starts to set. And again, on a cloudy day, you can see the sort of impact that yeah, the weather has on output as well. So that's where the variability of renewables does come in. Even if it's cloudy, they will produce a bit of power, but to get that real peak output, it does need to be pretty clear sunshine, um, as that hopefully that second graph shows there. If you this again is for a system aligned pretty much due south. If you had a system that was instead a roof with a different orientation that was east-west, half the panels on the east, half on the west, you would see a different shape. You'd see a big peak kind of around probably 10, 11 o'clock in the morning for the east-facing panel, then a big dip at lunchtime, or flattening off at least, and then another peak later in the afternoon. So again, that's something to consider, is getting the most value out of a PV system is the time of day that electricity is being generated and used as well. And again, looking at a wider time period of the annual profile of solar energy, you would see a similar shape actually, but just based seasonally rather than that kind of diurnal variation. So again, a year's worth of data, yeah, not much production kind of over the winter months when the sun is lower in the sky and the days are shorter. But then as spring comes, the days lengthen, the sun gets higher, then you start to see April, May, June, that production starting to peak again, um, through to August, September, and then it cycles down again. Interestingly, one thing you do probably tend to see the peak production in probably around May time, rather than midsummer, and that's because the temperature is affects the efficiency of solar panel systems quite a bit. They're probably at that optimal where it's bright sunshine but still slightly cooler. If they get too hot, then their efficiency does diminish slightly. So that's why you tend to see like May, September being the optimal months for output. June, July, August are still good, but you don't get that perfect bell shape because of the slight efficiency drop off. Okay, some of the costs, yeah, in terms of budgeting, how much we're seeing solar panel installation costs on the market at the moment. It tends to vary slightly by the scale of the installation you're aiming for. So for where you're looking at doing one-off smaller domestic systems, you could probably, as a rule of thumb, look at the cost of around £1,200 per kilowatt peak. So yeah, typical 3-4 kilowatt peak system would still be around, yeah, the 4,000, £5,000 mark. If you then scale it up to a rooftop, maybe more 50 kilowatts, you do see a slight saving from the economies of scale, probably more £1,100 per kilowatt peak. And again, increasing in size and so on, you do see the larger solar farms having their capital costs come down to £850 per kilowatt peak. And again, for interest, car park canopies in there, yeah, good useful space to use, but there's still a bit of extra expense there just because you've got that mounting system to mount the panels on. One thing social housing providers and other councils have started to do to benefit from these economies of scale is by aggregating lots of smaller domestic systems, you can kind of bring those upfront costs down just through kind of procuring equipment in greater volumes, and then also coordinating installation through timing, scaffolding, and more efficient allocation of jobs and workforce to pass on a few savings. Then the domestic battery system there as well, if you were to add on that bit of kit as well, it is an extra capital expense, probably £4,000 or £5,000 on top of the cost of the solar panel system. And again, how you use that battery would then determine how much of that extra investment you get back. I'll cover that in a moment. So conversely, on the saving side, there's three ways well, And in the current market, there's two ways you primarily benefit from solar PV and electricity. One is by consuming electricity directly, it's being generated, you're not having to pay to import that. So you're saving roughly 35p per kilowatt hour that you consume directly from the solar panel system. Plus, you get then an income from the electricity that gets exported as well, through things like the smart export guarantee. And depending on who your supplier is, you could get up to a further 15 pence per kilowatt hour for every unit that gets exported. So adding those two values together is roughly the overall income you get for your system. So this chart here has been produced by the Energy Saving Trust. It shows an average household system in the middle of the country at 3.5 kilowatts peak. And then the benefit, the financial benefit you get is pretty determined on how that building or that home is occupied. So someone who's going to be home all day running their appliances when the sun is shining is going to be financially better off, £610 in this case, over a year, just because they can offset that 35p income. Conversely, at the other end, someone who's out during daylight hours and comes home in the evening, that solar panel system will be meeting loads like their fridge, freezer, other appliances, but that but yeah, people who aren't into benefit from the solar panels wouldn't financially benefit as much. So in terms of payback, currently seeing 7 years according to their estimates there, and the worst case would be 11 and a half, but still pretty decent. In terms of the other benefit, the other driver, the carbon savings. So the UK grid is getting increasingly clean. It's currently around 200 grams of CO2 per kilowatt hour generated. And a typical home electricity consumption is about 3,300 kilowatt hours, or roughly 0.7 tons of CO2. So yeah, in terms of calculating the carbon savings, 1,000 kilowatt hours per kilowatt peak would save 0.2 tons of CO2. Multiply that up for a typical array of 3.5 kilowatts, and conveniently enough, you get to around 0.7 tons of CO2. So in theory, you could arguably offset your home's electricity emissions through investing in a solar PV array. It kind of matches up quite nicely with the current grid intensity. Okay, so some of the extra benefits you can get through smart solar systems. This is where you can either, you're using technology such as the smart meters, the smart switches, to benefit from the time of use that the power is being generated. So in this graph again here, the Energy Saving Trust have assumed that the home has a smart switch on an immersion heater that's able to dump excess solar energy into that home's hot water tank. There are other, battery does the same thing, and there are other thermal store technologies coming on the market that will do the same job. So, and increasingly smart diverter switches can send the power to where it's needed, whether that's, or to the best value, whether that's a battery, the water tank, maybe even an electric car, or exporting back to the grid, depending on how much the grid is demanding extra power. The virtual power plants as well there, it's not just the export value, especially if you have that fleet of batteries, assuming you had, say, 500 homes in your portfolio and each one of them had a small battery. There are companies that allow you to aggregate those dispersed batteries and have it act as if it's a single large one. And this allows you, as a kind of owner and operator of these batteries, to then bid in for flexibility income by offering grid balancing services both to the DNO and the national grid. So that's the business case, arguably, for having the batteries. It's not just to benefit the tenant, but to benefit the wider grid as well, by having that kind of flexibility income stacking in with the electricity production. A quick mention of how solar PV interacts with heat pumps as well. From previous rounds of, well, the Social Housing Demonstration Fund, and a bit of analysis that was done into the bids that came into that, pretty much all the councils that bid into it included PV in combination with some other energy efficiency measures as part of their bids. And yeah, PV and air source heat pumps do make quite a good partnership. Although solar panels do produce the bulk of their electricity in the summer months, where air source heat pumps are making their power primarily for heating in the winter, there are still some useful shoulder overlap periods in the autumn and spring where the PV can still kind of contribute to the space heating. And in the summertime as well, that PV can meet the house's hot water needs very efficiently through an air source heat pump as well. Just to remind us of that winter graph. So my home panel system at the moment is probably producing around 12 kilowatt hours per day. In winter, that would probably drop to 1 or 2 kilowatt hours, depending on how sunny it is. But even that into a heat pump multiplied up by a factor of 3 to 4 is still some useful heat energy going into either a hot water tank or the building. And again, that reduces the running costs of that heat pump for the tenant quite considerably. A few pointers on PV installation and maintenance. In terms of the disruption, it's not too bad. It's quite a short job in terms of people being on site. It can be done in a single day in terms of getting the kit on the roof and the rewiring done to the circuitry in the house. Scaffolding will be required just for safety purposes. That can, like if you have a coordinated work program, that can be mapped out in advance. In terms of safety, again, it's quite common to see now PV arrays having some form of caging or webbing around the edges, filling in the gaps between the array and the roof. In some cases, birds do like to nest and get under the panels, which some people don't mind, but it is arguably a safety hazard in terms of, and just for the operation of the system, there's a risk the birds could dislodge kind of wires and interconnectors, which would then obviously disrupt the supply of electricity. In terms of cleaning and maintenance, dust and other debris, bird droppings will affect output. Majority of systems should be sufficient with just rainfall to keep them clean, but if you're really looking to maximize your production, you might want to schedule an annual cleaning or more regular, depending on your location. The panels will generally have a lifetime of 25 plus years. You'd see that's quite a common warranty period, but you will need to look at the warranties for the inverters, because they will likely need replacing at some time within the lifetime of the system. They're usually guaranteed for 8 to 10 years. Generally, if you're doing the smaller grid connections under 4 kilowatts, DNO connection process is fairly simple. But if you are going to be installing a lot of solar PV in one postcode location, particularly if you're adding batteries in as well, I would recommend talking to your local DNO just to make them aware of the project and make sure that there's not going to be any issues in terms of overloading local substations. Yeah, early coordination with them is always worthwhile. Okay, final few comments just on the kind of tendering and procurement side. Entering into competitions like the Social Housing Decarbonisation Fund and other work programs, it's always good to go through the right processes to make sure you've got a good quality supply chain partner to work alongside. There's generally two common routes that councils can go through. One is dynamic purchasing systems, DPSs. These take out a lot of the kind of ODU level kind of tendering process off the onus of the local authority onto the DPS provider. So that's a kind of a pre-qualified list of installers and suppliers that you can access by purchasing into using that DPS system. It allows you to then run mini competitions to find pre-vetted suppliers and contractors to deliver your work programs in a fairly time efficient and robust process. Some common ones out there's Laser Energy have a consult, design, install DPS. So that can cover the whole range of a project from initial scoping and design through to installation. Some councils or providers have their own in-house teams to do the initial design, and then they only procure an installation partner. It offers you that flexibility. My hub team colleagues, they also run a regional DPS for the Southeast for our kind of hug and sustainable warmth programs. Frameworks as well. These are kind of more longer term specified time periods with pre-vetted suppliers. Common ones like Refit, Crown Commercial Services operate those. And if there's any particular deep dive into that, then yeah, recommend looking at the SHRA procurement toolkit, which there's a link there. I'll try and put that in the chat too. And Solar Energy UK last year also produced a procurement guide specifically looking at solar energy for local authorities, which I recommend taking a look at as well. Okay, thank you very much.